All right, good morning, folks. So this week's lab assignment is going to be very similar to the one we had last week. We're going to be using a circuit construction kit, but this time, rather than looking at alternating current circuits like we did last time, we're going to be looking, or excuse me, we looked at direct current last time. This time, we're going to be looking at AC circuits. So the simulation that we are going to be going to is going to be able to handle AC circuits instead of DC circuits. And we saw for the last couple of days that in an AC circuit, the frequency of our voltage supply is going to have a dramatic impact on the reaction of the circuit. And that's because capacitors and inductors both contribute something that is similar to resistance called reactance. But the reactance of something is dependent upon the frequency. In the case of capacitors at low frequencies have a very high reactance. They act like a very large resistor at low frequencies, but at high frequencies, they hardly do anything. By comparison, inductors are the other way around. Inductors have a large reactance at high frequencies, but as the frequency gets lower and lower and lower, their reactances decrease. And in order to find the total resistance of an AC circuit, you have to compute something called the impedance, which is the way that we combine resistance with the reactance of the capacitors or the inductors. And so what's going to happen is that reaction or that relationship ends up being pretty complex. And that means that the amount of current that you get is going to change as you increase or decrease the frequency of oscillation. And so that's our goal today is we want to figure out the functional relationship between the frequency that we've chosen and the amount of current that we get in response. And we could derive that theoretically if we wanted to, but what's going to happen is it would be really, really, really ugly. And so we're going to do something that we often do in physics, which is we're going to cheat. What we're going to do is just find the function phenomenologically, by which I mean we'll take some data, we'll get some kind of graph, and we'll try to find a function that fits that graph as well as possible. And we're going to use that function once we found it in order to interpolate and figure out where certain breakpoints will occur. So let me kind of, get a bit more concrete because I suspect that that's maybe going over some of your heads. But once you see it in action, it's going to be super simple. So look, here's the AC circuits simulation, and I've built myself a series RLC circuit out of it. Now, one thing you'll probably want to make use of, because the minute that I hook this battery up, I'm going to start charging up my capacitor and inductor, and I'd like to start from a fresh slate every time. But in order to make that happen, I end up installing this little switch here. So when I click this switch, it will close it. So right now I have the switch open, so there's no current flowing. Nothing is happening right now. But as soon as I close that switch, stuff's going to happen. Now, you can see that as I've closed that switch, I now have an alternating current flowing through this circuit. Plug myself in before my battery gets too low. Now, one thing I will caution you, and I have already made these changes myself, is that the default values for the resistance or the capacitance or the inductance, all of those default values are probably not what you're going to want to go with when you build your circuit. You'd like to be able to have your current be large, and that means you're going to have to make some changes. So you'll need to design for yourself what value of your power supply voltage you use, what value of the inductance, what value of the capacitance you use to get a response. If you just use the default values and you hook it up like I have it here, you're going to see very little current. And it's going to make it really, really hard as you go through and change some of these frequencies because the current's going to get so small, you're going to have a hard time measuring it. So think it through, decide what values you're going to want to use based on the size of your observable currents. You'd like to make those currents as large as possible, so that's going to mean that you're going to want to probably make adjustments accordingly. But once you get a circuit that's up and running, you could do what you did last week. If you wanted to measure, say, the voltage across something or the current through something, you could apply a voltmeter. Now, the problem is, if I put this voltmeter, say, across my capacitor, so that I'm trying to measure the voltage across my capacitor, you'll see that the voltage value that I get keeps oscillating up and down, which makes this impossible to read. This sucks. So in order to get a good measurement, in the real world, we would use an AC voltmeter, which basically takes measurements over a certain period of time and averages them to find an RMS voltage. But for some reason, this simulation doesn't have something like that. So what we're going to have to do is kind of do it ourselves. And so what I have here is a little voltage chart. And you can do something similar with a current chart. And in each case, what's going to happen is, if I wanted to measure the voltage across something, I could put the leads across it the same way I would a voltmeter. And what you'll see is that I've got a sinusoidal graph that I can then look at. And if I zoom it in, well enough, I can get a measurement. And I can see that this appears to be oscillating between, say, plus or minus 20 volts for my inductor, or that's my capacitor I'm measuring across. I can do the same thing with my current. I can apply this anywhere, and since these are all in series, any place on the circuit will work. I'm going to put it right here. And again, you can see that right now I'm getting a current that looks like it's oscillating between plus or minus about 5 amps. So I'm measuring the peak current to be about 5 amps. And if I know I max, I can always calculate IRMS, because IRMS is going to equal the maximum current times about the square root of 2/2, which is about 0.707. So just based on this, at the particular setting that I'm at right now, I have a data point, because I'm oscillating my thing at some frequency, and I am getting a current in a certain amount. Now, if I go over here and change my frequency from the 0.5 hertz that I'm at right now down to, say, let's go 0.2 hertz, what you're going to see is that the current that I'm getting in response is considerably larger. And that's going to be a secondary data point. So what you're going to want to do is to measure the response as a function of frequency, change the frequencies, and hopefully be able to get a graph of what the currents are as a function of induced frequency. So one thing you're going to want to be on the lookout for is that this simulation is remarkably finicky. Some of that is because this is the HTML5 conversion of an older simulation that the PhET site hosted that used Java, and they're trying to replace that with HTML5 so it can run in your browser without having to download any stupid plugins. But unfortunately, it's a prototype. It's not quite ready for prime time, but they rolled it out early this past spring semester when the coronavirus hit, because they thought that people like myself might need them, and they were right. So sometimes I think it might be a little bit weird and buggy, and so there's some things you probably want to look out for that tells you, boy, this thing's acting strange. So, like, watch this. I'm going to close this circuit, and you see how, like, it does this weird kind of it takes a moment for it to kind of settle down. Be on the lookout for that. Let it settle down first before you take your measurement, so that right now you can see that at this frequency, I have a peak current that's somewhere in the neighborhood of just under 0.1. Notice sometimes you get like weird little jumps. I think that's a bug in the code. So let it settle down before you take your measurement and try to ignore the random little weird peaks. I've also noticed that if I switch tabs and I come back, sometimes while the tab is closed, it does really crazy stuff. So be aware that that's something that it can do. When you switch away tabs and you come back, you may come back to something that's acting a little bit crazy. Also, when you go to change your frequencies, what I would suggest doing is before you change the frequency of your power supply, I would suggest opening the switch, and you see how there's a little bit of charge left on the capacitor. You can see the blue and the red dots there. If you click on the capacitor and discharge it, you can empty it out. You should probably also empty out the inductors as well. You shouldn't, in principle, need to discharge the inductors, but again, I'm not sure if the simulation is quite perfect. And so now when I put it back, I'm not going to have any of the residual effects from the charge that was on the capacitor to begin with. If you simply take this and drastically alter your frequency, what's going to happen is it tends to behave very erratically because you've got an additional source of voltage besides your power supply, and that causes it to drift in a difficult to manage fashion. So just be aware of that. So in any case, what's going to happen is when you take your data, you'll have several values of your input frequency, and you'll have several values of the peak current. I went ahead and did something here where I took a whole bunch of frequencies and I tried to get a lot of them because I wanted to go over the entire range, and I got an entire set of currents. And if I'm looking for a functional relationship, that means I always want to look to see what the graph looks like. So you can see that what I'm getting here is a graph that looks pretty doggone complicated. Now you expect that at the resonant frequency or around the resonant frequency, your impedance should be as small as possible, which means you should get a very, very large current. And that's why you'll notice in this graph, really? Oh, there we go. There we go. So you'll notice at, All right, service pad is connected. All right, for some reason my pen isn't working. It's making me very annoyed. So look, if you notice, okay, darn it. I'm just gonna have to do this the old-fashioned way. If you look around here, you can see that I have a local maximum for my current. That means that I'm at or around the resonant frequency. However, if I go below that frequency, you'll see that the current starts to dip. You definitely want to choose L and C in such a fashion that your resonant frequency occurs somewhere within the range of frequencies that you have available to you at the simulation. The simulation could go down as low as 0.1 hertz and as large as 2 hertz. And if you use the defaults, you're not going to see that local peak. I need you to see that local peak. We want to be able to show that there is a resonant frequency, and at that resonant frequency, I get a very large current. But at above or below that frequency, I get a dip. And I was able to achieve that here. You can see I have a local maximum, but my graph is something complicated. And so what I would like to do is to figure out what is the equation that governs this, or at least come up with a good approximation of it. And then from that, the question that you're being asked to answer in the lab is, at how far above or below the resonant frequency I have to go before the current gets reduced by a factor of 2, 4, or 10. So you'll notice I have this weird nonlinear graph here, and I am hard pressed to come up with an equation that looks like this. And it's certainly not going to be one of the defaults that Excel would use in its curve fit algorithms. So if I try to add a trend line, what's going to happen is I'm going to have a difficult time getting agreement. Obviously, a linear trend line is stupid. That doesn't work. But exponential trend line, it doesn't really agree very well. Look at how different this is from that data point. That's not great. Logarithmic curve, again, doesn't fit very well here. Even if I go the polynomial curve, and crank the order up, you can see I get weird behavior. And that's really unfortunate. Power series, none of these defaults are going to fit very well with my actual data. And one of the things that physicists will often do when we have complicated expressions and we're trying to figure out what the equations are, but we can't come up with a quick and easy, simple way of doing it, is sometimes we'll find a fit that works well with just a fraction of our data. In other words, what if I instead imagine that I have one equation for the high frequencies and another equation for the low frequencies? That's maybe an easier fit to make. And what I notice is that for a graph that looks like this, I might imagine that this, from here on out, imagine I could draw a straight line, I can't. Imagine that that's like one equation. And then on the other side of the resonant frequency, I'll change colors for this. Imagine that the other side of the resonant frequency, I have a different equation. And so the idea is if I separate my data into two sections and I only do a fit for the big side versus a fit for the small side, I might have a better amount of luck for figuring this stuff out. So you're going to need to know, how could I do that? How could I fit only a section of my data? And here's how I would do it. If you look on this graph and I right click a data point, one of my options is select data. And if I go in here and edit this series, you'll see what I'm doing, right? Here are my X values. The X values on this are coming from column B. So there are my frequencies. The Y values are from column C. That's my currents, which is what I expect. The problem, though, is that I'm using the entire set. For the X's, I'm using all the X's all at once. What I would like to do is to not include this one data point where it starts to dip back down. That's, in my case, it's cell B6 because I took them out of order. So what I would do is I'm going to go in here for my series X values, and I'm going to choose all of those. I'm going to hold down Control so I can highlight things that are not adjacent. Oops. Let's try that again. So I'm going to go, I'm avoiding this one here. So I'm holding down Control. And I've highlighted all of the cells that are not the one that I want to exclude. Okay. That's being annoying. So before I do that, let me solve my problem real quick. I'm just going to sort. There. I just sorted my values so that they're in ascending order. That's going to make my life a little bit easier for this. I thought I could do it with a careful control, but apparently I cannot. So I'm going to go to select data, edit. This time, however, instead of selecting the entire set, I'm going to exclude that small data point. And for the Y values, I'll pick the corresponding set. So I'm excluding that very first data point. And of course, when I do that, I get this nice, happy little curve. Now, unfortunately, that means that I just took that one data point where I'm below the resonant frequency and I've taken it out of my graph. And that kind of sucks because I'd like to show up on my graph. I just want it to be a separate data series. So what I can do is I can add a second series. And for that second series, for my X values, I'll just use the ones that I took out. And for the Y values, I'll use the ones that correspond to that. So you can see now that what's happening is the data point is still there, but I can tell that it's a different data series because it gave it a different color. And if I really, cared that much about that, I can even, go back and format that data series. And, I could change the color back to, where is it? Oh, I see. Either way, the point is I can tell now that I have two different data series. I thought I could change this to match colors, but apparently I can't. It wants to keep them separate so that you can tell at a glance that it's not the same series. But now when I go to add a trend line, I'm only fitting a trend line to this one section. And so now if I go to say something like a polynomial fit and I crank the order up, I have much better agreement without a whole lot of weirdness. And so I can come up with a fairly decent approximation because I'm not trying to fit that orange data point in with all the others. So I can have a much simpler value. Let's go with, yeah, that's too many local minima at that point. So you can see I can now get a decent approximation of what that function is. And the cool part is that now if this is the function that governs what current I get as a function of frequency, so in this equation, X would be my frequency and Y would be my current, I can then start to make some guesses about where things would go down by a factor of 10 or whatnot. So that's your goal, is to figure out what that function is as a function of frequency and then use that function to help interpolate. If I wanted to do that, I mean, like for instance, in this case here, I'm using a fourth order polynomial. And so if I wanted to know like at what value of frequency do I get 1/10 of my original current, that's a really hard problem to solve. That's an algebraically difficult problem. But you could, try playing around with it and find a value that way. For instance, what I would probably do if I wanted to find at what value of frequency, that's X, do I get 1/10 of my original current? Essentially what I would do is I could take that function and so like here's F and here's my corresponding I. My cell here, what I'll do is I'll take that formula. So 2.8267 times my frequency to the fourth power minus 17.204 times my frequency to the third power plus 38.63 times my frequency squared. So minus minus 38.694 times my frequency plus 16.27. So what's going to happen is if I take a frequency of, let's say, 0.1, there's my current. If I take a frequency of 0.2, there's my current. And I know that like at 0.2, I get about 10, which is, that makes sense because that's what I had in my data. At 0.1, it would be up here somewhere, but obviously that's not what the real equation does, which means this function is only valid for things that are higher than 0.2. We wouldn't use it for things lower than 0.2. The equation is something different in that range. However, if my peak current is 10, well, how far do I have to go until I get down to 5? Well, if I go down to 0.5, that's pretty close. 0.6, nope. 0.7. Wait, what? Oh, that's why. All right, I have a typo or something because clearly my function at f equals 1 should be something close to 2, and it's not. That's a point. There we go. So let's try that again. If I go at 0.2, it should be about 10. Yes, it's about 10. So now I'd like to have like 1/2 of my peak current. That's one of your goals. So let's see what happens where I have to go to get to 0.5. All right, there's 5. So let's go back to 0.4. That's a little bit too big. How about 0.45? How about 0.43? How about 0.47? How about 0.48? So yeah, you can see here at about a frequency of about 0.46, I have about half of what I started with. So there's one possible value. All right, so how did I do that? I made my graph, plotted my graph, found a function that fit to it, and then what I'm looking for is at what value of f do I get approximately half of my peak value? And that required me to play around with it a little bit. So I couldn't solve it in closed form because the algebra is just too difficult. But this is why we have computers, right? Computers are able to solve these sort of problems for me without too much of a hassle. One trick you can do to make your life a little bit easier and not you have to use trial and error is that once I have this function set up, there's a thing in Excel called the solver, which if you've never used it before, it might not be currently active in your version of Excel. If you go to your File tab and look under Options, it's one of the add-ins. And if you have it turned on, you'll see it under the active application add-ins, but more than likely, if you've not used it before, it's probably going to be in this list of inactive add-ins. If that's the case, you can turn it on by hitting Manage Excel Add-ins, hit Go, click the checkbox. Obviously, mine is already checked because I have it turned on. And once you've done that, if you go to your Data tab, you'll see a little button for the solver. And what the solver allows you to do is to optimize certain values. So for instance, if I go in here and I turn on the solver, the set objective cell is the cell that I'm trying to make be a particular value. In this case here, maybe I'm looking for, at what value of the frequency do I get half of my peak current? Well, my peak current was 10 amps. So I'm looking for a value of 5. So what I can do is I can hit, for my set objective, I'll hit this, the thing I've been kind of playing around with, and I'm trying to optimize that cell to be a particular value. I could try to make it a maximum or a minimum, but I'm going to try to make it be a specific value, and I'm going to look specifically for 5. And I'm going to give Excel permission to change certain variable cells. Well, I'm going to give it permission to change this number. If I do that and hit solve, what Excel will do is it'll play around the same way that I was playing around, and you can see that what it has done is it's found that you can get the closest possible to 5 using that function with this value of f. That's awesome. I can keep that solver solution. What if I was looking for 1/10? Well, if I'm looking for 1/10 of my value, all I have to do is take that and make that be, oops. I can go back to my solver, and this time what I'll do is I'll optimize that same cell, but now I want it to be a value of not 5, but 1 by changing variable cells. And you see that it yelled at me. Why is that? So why did it yell at me? Well, because I've got this annoying constant term right here. So this particular curve is going to end up leveling off, but it won't level off towards 0. So what I might have to do is try going back and adjusting my fit and getting a fit that doesn't that converges a little bit better. This is not the best fit for doing that. So I'm not going to have a very solid response for that. Let's try that again. Maybe I can make some. Oh, that's why. Never mind. That's why it went crazy on me. Oh, there you go. So you can see there, at a frequency of just over 2, I'm at about 1/10. And so you can do that kind of stuff to play around so that you don't have to do it by hand with just trial and error. All right. So hopefully that makes sense to you guys. And again, what is your goal in this lab? You want to be able to come up with the function for how the AC circuit varies as a function of frequency, and then use that function to determine how high above or below the resonant frequency you have to get in order for the RMS current in the circuit to decrease by a factor of 2, 4, or 10. All right, so hopefully that's pretty clear. If you have any questions about how to set this up, by all means, come talk to me and I can walk you through it. But that's ultimately your goal. So hopefully that's enough. It sucks that nobody's here to ask those questions, but I think you guys do this. Good luck, and I'll talk to you on Monday.